Welcome to our session, How to Build Codex Solutions. My name is Ryan Vollum. I'm a principal software engineer in Microsoft's Office of the CTO, and I've spent the last couple of years working with these large language models like GPT-3 and Codex.
Yeah, and I'm John Mallison. I'm a software engineer in commercial software engineering here at Microsoft. I've been working with OpenAI's models, specifically Codex, for the last 6 months, and I'm really excited to be sharing our findings to accelerate your experimentation and learnings with these models.
Yeah, and the goal of this session really is to distill our learnings into 30 to 40 minutes to help you get started with these models and have you hit the ground running.
And we found the best way to really learn with these models is to actually get in the playground and see what they are capable of. So this is going to be mostly a demo-heavy session. We do have one slide to start with that's going to go over some really helpful links for learning about these models.
Yeah, so the very top link here, for all Build attendees this year, 2022, we are providing free credits to use models like GPT-3 and Codex. We absolutely advise that you go use these credits. These are some of the world's most capable machine learning models running on huge supercomputers, and we'd love to see what you're able to build with these. There are also a couple links here for the OpenAI Playground, which you'll see extensively in the upcoming demos, and then for the OpenAI API documentation.
Yeah, and beyond prototyping, we're also hosting OpenAI models on Azure to support production solutions. The Azure OpenAI service offers the latest OpenAI models with Azure's security, compliance, privacy standards, and enterprise-grade features that customers need to build and run production services in the cloud. Check out the link on the slide in order to learn more about that offering.
And then last on this slide, we're super excited to open source three prototypes that we've built with Codex. One takes natural language and produces code to generate 3D scenes. The second here takes natural language and uses it to generate command line commands in PowerShell, Bash, and Z Shell. And the very last one uses Codex to power a non-player character in Minecraft. So as of today, those will all be available and open source on GitHub for you to pull down and start prototyping with. So the session is primarily about Codex, but we do find it's very valuable to start with its predecessor, GPT-3. So our first demo here, we're going to be talking about how to use GPT-3 to coax the model to handle a wide variety of language scenarios. Generative language models like GPT-3 are trained on a very simple task, guessing the next word in a sentence, or, more generally, the next token in a sequence of tokens. They're so good at doing this that they can continually guess the next word, producing whole sentences and paragraphs that look indistinguishable from human written text. We're looking at the OpenAI Playground where we can test models like GPT-3. We pass a prompt, in this case the passage I just read here, and ask the model to produce new tokens, in this case words. You can see the model output new words here, and as it writes, note that what it's writing is semantically and syntactically correct, and seems to be following the style of the passage that I gave it. This is an example of GPT-3 generating prose, specifically prose about itself. While compelling from a demo perspective, this is far from the most useful way we can use these models. Let's move over to another prompt to show how we can coax more specific behaviors out of GPT-3. In this prompt, we're passing GPT-3 a complex scientific entry from Wikipedia about the Lagrange 2-point, the place where the Earth and Sun's gravity are equal and therefore cancel out. Note that at the end of this passage, we added the text, "Explain it like I'm 5." If we submit this, we'll see an output from the model that effectively summarized the technical text into a much simpler explanation. And sure enough, the model wrote a couple sentences here that much more concisely and simply describe what the Lagrange 2-point is. Like before, we really just asked the model to guess the next chunk of words, but we crafted our prompt in such a way that those words would be a simple summary. The discipline of crafting prompts to coax specific behaviors from models like GPT-3 is called prompt engineering, and we can use it to coax many other behaviors as well. In this next prompt, we ask GPT-3 to translate a sentence, "What rooms do you have available?" into 3 languages. Having been trained on a large corpus of internet data, GPT-3 has seen enough languages that it's capable of translating between them. I'll submit. And sure enough, the model successfully translates the passage into Spanish, French, and Japanese. Let's try another prompt. In this prompt, we give the context that the model should chat as an AI assistant. We include some high-level context. The following is a conversation with an AI assistant. The assistant is helpful, creative, clever, and very friendly. And now we should be able to say new things to this assistant. I'll say, what's your favorite color? And we'll go ahead and submit this. And sure enough, it responded blue. Now I'll say why. And it was able to follow the context of the dialogue to understand my question and answer with a meaningful answer to why its favorite color was blue. By appending our conversation onto an existing conversation, GPT-3 can generate context-aware dialogue. In this example, I'll quickly note that we set a stop sequence here, both for human colon and AI colon. And this ensures that the model only generates one dialogue response at a time. If the model ever generates human colon, it'll go ahead and stop producing language. This keeps it from continuing this dialogue infinitely and lets it know when it is our turn to go ahead and take over the dialogue. What if we tried a different prompt where the AI agent is bored, surly, and unhelpful? Let's try this again. I'll say, what's your favorite color? And sure enough, it gave a fairly surly answer. It said, I don't have one. And I'll say, why not? And it totally stayed in character because I'm a machine and I don't have emotions. So by tweaking our prompt describing the dialogue, we were able to coax the model to follow different characters, to emulate a different character in this case. Let's show one last prompt here. In this prompt, we use a slightly different technique to coax specific behavior from the model. We explain that we want GPT-3 to classify companies into a set of industries. And you can see that we give it examples. These examples demonstrate to the model exactly how it should perform the task. If we add a new company, like Microsoft, it should create a comma-delimited list of categories that Microsoft works in. And sure enough, it handled this successfully. In this case, you can see that we set the stop sequence to a line break. This will allow the model to only produce the categories for a single company versus writing more companies and more categories on its own. Giving examples like this of what we want the model to do is a technique we call few-shot prompt engineering, and it's a great way to ground the models in exactly what you expect from them. All of these examples demonstrate that we can coax all kinds of behaviors: prose generation, summarization, translation, chat, classification, and more from models like GPT-3 through this larger discipline of prompt engineering.
It's amazing that by controlling the context passed into GPT-3, the same model can be used to summarize text or translate or act as a chatbot. There's a lot of flexibility in the model.
Yeah, we've had models in the past that can accomplish some of these capabilities, summarization, translation, but they're usually one-off models that have been custom built to those tasks. What's so impressive about GPT-3 is it can handle any of these tasks just out of box. And you also don't have to be a data scientist to use these models. You don't have to custom train them, and you can really use them if you just understand human language.
That is impressive. And it really does shift kind of understanding and being able to generate these impressive results into a matter of creativity and structuring a prompt in a specific way.
Yeah. Now, one thing I didn't mention in that demo, we talked about some of the parameters with these models. We specifically mentioned the stop sequence. There's another parameter that's extremely useful when interacting with these models, and that's temperature. Temperature is the little knob that you can turn between 0 and 1 in the playground, and that dial determines how random the model will be. If you make the temperature much higher, closer to 1, it will inject some randomness into the model. This means the model will likely take more liberties. It will likely be more creative. And higher temperature can be useful for creative scenarios like writing, for example, where you might want to get suggestions from a model that do try new things. I'll note that for the rest of the demos in this talk, we do keep temperature at 0 because we want the model to behave completely deterministically. We want the same input to always produce the same output.
Yeah, and I mostly work with Codex where we are writing that code, and I do value some of that determinism of a low temperature, but I do find that even there, it is helpful to kind of turn the temperature up every once in a while and let Codex generate a couple responses just to see kind of the variety of what it can do. With that, let's shift into a demo where we actually talk about Codex, which is a version of GPT-3 that's been trained on GitHub, so we can use it to generate valid code. In this demo, we're going to take a look at Codex, which is a version of GPT-3 that has been trained with GitHub. This means that it understands the vocabulary and structure of a variety of coding languages. In the playground, I'm going to switch my engine to point to Codex, and to show that this still behaves in the way that GPT-3 does, I have a general statement here, and I'm going to hit submit to continue generating text. Codex generates. It was created by OpenAI, a San Francisco-based artificial intelligence research laboratory. This is very much in vein with what GPT-3 would do. But Codex has seen a lot of code. So we're going to use a slight modification on the basic example for Codex, create a JavaScript dictionary of 3 cities and locations. We go ahead and hit submit, and we see a dictionary being created with our 3 cities and the latitude and longitudes for each of those cities. I'm going to continue on, and let's say add Seattle to this list. And Codex predicts the correct code. It adds Seattle to that dictionary. One important thing to note here is exactly how we're providing this natural language to the code. In a lot of code files, a lot of GitHub, natural language tends to appear in comments. So for JavaScript, one way to do a comment is a /*. And this way, Codex is expecting that after this, there's probably code that's following. So to show this in action, let's say create a Python dictionary of 3 cities and locations. The Python comment is a hashtag, not a /*. So let's see what happens. This is not what we would expect when we said create a Python dictionary. It's creating PyObjects, and it is still doing the correct actions. But this is in the CPython SDK for C++. C++ uses /* as a comment, meaning it's more likely that the code that should follow is of C++ than it would be of Python. To switch over to Python, we need to switch our comment character to the hashtag. I'm also going to add it as a stop sequence so we don't generate too much code, and go ahead and hit submit. In this case, we generate a dictionary, 3 cities, and their locations. Let's make something a little bit more interesting. Write a function that counts the number of locations with a U in them. And let's see what Codex generates. So here we see that we have a function called countU, initializes a count. It then loops through the passed in dictionary's values and adds to the count if a U is found in location. This is correct code that's been generated off of our natural language. Codex can also generate natural language off of our code. So I'm going to copy this function out and go to another tab where I've defined a little bit of a template. So a chunk of Python code, which I just pasted over from the first one, and let's see a 1-line explanation of this code. Go ahead and hit submit. In this case, Codex generated a stop sequence immediately, so I'm going to remove that and generate again. And it says, this function counts the number of locations in a dictionary that contains the letter U. This is correct. So I'm going to clean up the over-generated piece. I'm also going to change the output format so that it is what I would expect of being a string, add back the stop sequence, and now let's see if I can use this same format to define something else, define a different piece of code. So for this one, I'm going to write foo, take a variable a. I'm trying to be intentionally obscure so that Codex can't clue into the semantics. And let's say return join reversed string of a. So we're going to stringify a, and then we're going to reverse it. And let's see what Codex generates to describe this function. This function takes a string and returns the string in reverse order. That is correct. One more example to show that Codex is focusing in on what the code is doing, not necessarily the names, is what happens if I try to deceive the model and I call it convert to string, but the action that I do is actually divide by 1.8 and add 32, which is how you convert from Celsius to Fahrenheit. I'm going to go ahead and run this. And we see that Codex successfully predicts this function converts a temperature in Celsius to Fahrenheit. This shows that Codex is looking at the structure of the code, not just the names of the variables and the functions, to determine what's actually going on.
So what I love about your examples here is that just by providing a few examples to Codex of the kind of code to NL you wanted to produce, Codex really keys in on the appropriate output format. You'll note that this is very similar to the examples we gave with GPT-3 before that helped coax a specific output format for classifying companies. In this case, it's the same for code.
Yeah, one thing that I really want to make sure is clear is that Codex is the same model every time we call it. So we're talking about it learning, we're talking about teaching Codex things, but really it's just this context that we're passing in that's changing the behavior of Codex as it outputs. But Codex is stateless. It's the same model every time. So it's all through this context where we're actually teaching new skills to Codex.
Yeah, that's a really good call out. I myself have often felt like as I interact with the model, it is actually learning. But really, the only thing that's changing is our prompt. The model is truly stateless.
Which is an incredible thing about this model, where if you have a back and forth with it, where you're adding information, it's able to reason over that past information and create intelligent completions for what you want next.
Absolutely. Let's go ahead and roll to the next demo.
In this demo, I'll show how we can use Codex to build 3D scenes using natural language. Specifically, I'd like Codex to produce code for a web-based 3D rendering library called BabylonJS. I'll start by giving the model context. I'll say, the following are natural language comments, and the code needed to accomplish them using the BabylonJS library. And I'll try my first command. I'm going to say make a cube and see if Codex knows how to do that using BabylonJS. And remarkably, it appears that the model already knows how to use the BabylonJS library. Because BabylonJS is a very popular OSS library, the model has already seen enough Babylon code to work with it. Now, it seems like it actually passed some parameters here that are optional. I wanted to just use the default size for a cube, and I'll go ahead and remove the scene there since that's totally optional. And we'll try a second command. I'm going to say make a sphere on top of the cube and see if the model is capable of doing this. And sure enough, it created a sphere. It looks like it made its diameter 2, and again, it passed scene. I'd rather not do that, but it went ahead and created the sphere, and it knew to make the sphere's vertical position 1, which positions it on top of the cube. This is great so far. Out of box, Codex clearly knows how to use BabylonJS. Now, I actually wanted to have it produce its code a little bit differently, though. Instead of saving these objects as variables, I'd like to save them on a state store that we can keep track of and refer to later. So I'm actually going to go ahead and declare a variable here called state, and I'm going to make it an empty JavaScript object. And instead of setting these variables, I'll have them set on this state bag here. So I'll say state.sphere and then state.sphere.position y equals 1. And this will allow us to refer back to these objects on this one communal state bag in the future. Now, let's see if we can go ahead and make these, the cube and the sphere, different colors. I'll say make the cube red and the sphere teal. And I'll go ahead and submit here. And excellent. It went ahead and created a new material for the cube. And it went ahead and changed that material's color to what it knew was red. Similarly, it was able to do the same with the sphere, and it set that as teal. So this worked as expected. And you can also see that it was referring to these things as they are saved on the state bag. So sure enough, it was able to use this context of everything that happened before to recognize where these things were saved and where it would have to update them. So by interacting with Codex in the playground, we were able to figure out what it could do and what it couldn't do with the Babylon library. We also found that by giving it a few examples of how we wanted our code, we were able to coax very specific code from the model. We can use this programmatically to enable real-time 3D generation by simply calling the API with the prompt that we've built here and adding new commands and asking the model to generate new code. Let's shift over to the browser where we can see this in action. Just as we saw in the playground, this prototype will use Codex to turn natural language commands into BabylonJS code. The only difference is that this web application will actually run that code to create a 3D scene. I'll start simple. I'll say make a red cube. And the model will produce some very familiar code to create and render this cube. And sure enough, we now have a 3D cube that we can interact with in this scene. Next, I'll say add a teal sphere above it and another below, and see if the model is able to create and position these spheres accordingly. And sure enough, it created this sphere of the right color and it positioned it accordingly. Now, this is a very simple example using Babylon primitives. We've found the model can also compose these primitives into more complex creations. So I'll say make a chessboard using black and white cubes. And Codex, understanding the semantics of a chessboard that's an 8x8 grid, and knowing how to write the code to represent that, is able to successfully create this chessboard using some very elegant and fairly concise code. So now we've got this 3D chessboard that the model was able to successfully create. Let's try something even more complex. I'm going to say make the background black. And the model knew how to do that. And then I'll say create a model of this solar system. And this will require Codex to know the relative size of planets, their positions, their names, their colors. It has to tap into a bunch of outside knowledge and also a bunch of coding knowledge to go ahead and create this model of the solar system. And sure enough, Codex wrote a ton of code here to create a sun and 8 planets, which is unfortunate for Pluto. It looks like it did not make the cut this time around. And so, yeah, the model was able to borrow upon its knowledge of the world, or in this case, the solar system, and its knowledge of how to write code to create this fairly complex scene. Now I'll say add a few hundred stars to the scene. And it looks like I had some misspellings here, but the model should be able to read through that. And you can see it wrote a for loop to scatter stars around randomly and approximate the look of stars. And then I'll say I'll say add rings to Saturn, and the model should be able to approximate a shape for rings so they can wrap Saturn in. And sure enough, the model decided to use the BabylonJS torus primitive to wrap Saturn in rings. So we were able to build this fairly complex 3D scene using nothing but natural language, just by giving Codex a few examples of the kind of code we wanted to write. I'll note the prompt that we used here had no examples related to the solar system, no example related to planets. Codex out of box just knew how to do this.
In that demo, it was really great to see how good Codex is working with Babylon right out of the box. Working with GPT-3 or Codex, it's really about trial and error, kind of testing and seeing what it can do originally, and then also nudging it in the right direction when it's creating the wrong completion.
Yeah, I'd say working with these models is really a bit of an art and a science. We strongly advise spending some time just interacting with them in different ways to see what they can do. When they're wrong, you can provide examples of what you would have liked them to do instead, and they'll often generalize very quickly from just a few examples.
Yeah, and I know personally I've been really surprised at what Codex is able to do out of the box, where it makes some very complex completions that I wasn't expecting it to be able to handle. And then in other cases, it seems to get confused. And then those few examples really help put Codex onto the task that I specifically want for it to work with. Playing with it really is the best way to get an understanding of what to expect.
Yeah, absolutely. In this scenario, we saw clearly that the model was very good at producing BabylonJS code. It's very clear that there was probably a ton of BabylonJS code in its original training set. But what if Codex has never actually seen the API or library that you wanted to produce code for?
Yeah, let's take a look at this next demo where we play around with Codex and teach it the Minecraft bot API, which came out after Codex was trained. So we know it has not seen any of this data. In our previous examples, Codex had seen both the language and the libraries that we were asking it to generate in its training data. In this example, we're going to look at the Minecraft Simulated Player SDK, which is a JavaScript package used for automating actions on bots in Minecraft. This SDK was published after Codex was trained. So I'm going to switch to this next tab, where we have a comment that sets the scene. This file contains Minecraft bot commands and the code needed to accomplish them using the simulated player JavaScript library. We're also giving a little bit of information to say, if asked something conversational, the bot should use bot.chat to answer. So to start off, let's use a conversational prompt, what is the meaning of life, and see how Codex responds. So we can see that bot.chat is the correct generated answer, and Codex wrapped this inside a chat add pattern. This chat add pattern is not something that's in the SDK. The SDK uses bot.chat directly. So what we'll do is we'll clean up this generated response and leave this in a growing set of context. So what we'll do next is ask, what movie is that from? And when Codex goes to answer this question, it has both our initial prompt, plus it has the added context from the first answer. So here we would expect it to say bot.chat, Hitchhiker's Guide to the Galaxy. So we can see how Codex is pulling from that rich language understanding, and it's combining the bot.chat syntax from the example that we gave it. Let's try something a little bit more complex. Let's say move forward and see what Codex does. Codex takes a very good guess here. It's learned from our previous examples, bot.something is what we want, and it made a good guess at move forward. This isn't how the SDK was implemented, though. It was actually move relative, where this first flag is for left, right, and the second flag is for forwards, 1, backwards, -1. I'll leave this in the context and ask Codex to generate move backwards. So what we would expect is Codex is able to learn from the example that it previously had and successfully say, okay, if I want to go backwards, it needs to be -1. What we're building here is what we call few-shot context, where you give Codex a couple examples of it doing things similar to what you want to do, which gives it more information when it goes to act on the new task. To show this in action, let's ask it to do something it hasn't seen, like move left and forwards. So Codex had not seen left, but it was able to make the guess based on the previous ones that this first argument is probably left-right, and left would be -1. This process of building up these few-shot examples is clearly having a good impact on Codex's predictions, but it is a slow and iterative process. I'm going to switch tabs, and what we're doing here is we're providing the API reference on top of that initial comment. So here we're providing information about what this API actually looks like. We have move relative with the left, right, back, forward, and also a parameter speed that we didn't see in the previous example. We also have stop moving, look at entity, and jump up. The benefit of providing information to Codex in this way, the API reference, is that an API reference is something that is built with all SDKs. This is a much easier way to provide information and context to Codex than to manually build up a set of examples. With this in context, let's go ahead and start with our first example, move forward. Hit run. And in this case, Codex still thinks that we should be using this onCommand method to call move relative. I'm going to go ahead and correct it in this case so that Codex knows how to work with this API. And let's go ahead with a more complex case. Let's say move to the left and backwards at speed 3. So we can see that with a combination of the parameters in the API reference, plus the single example of how we call this API, the move forward example, Codex is successfully able to figure out how to move left, backwards, and with some speed. We can also try to jump, which we would expect Codex to be able to pull successfully from the API reference, as it does. We can also ask it to do more complex things. What the API reference is saying is move relative starts the player moving in a direction, and then to stop them moving, you have to make a second call. So what if we say move to the right for 3 seconds? In this case, we would expect a command to start us moving to the right, but then we also need another command that happens 3 seconds later to tell it to actually stop moving.
So we've seen several different ways we can use the Codex model. I think in general, the scenarios fall into one of three buckets. Either we're using natural language to generate code, we're using code to generate code, or we're using code to generate natural language. Now, some of the scenarios we looked at were NL to code related. You can use natural language to query a database, or to control an agent in Minecraft, or to speak 3D objects into a scene. We see these natural language to code scenarios as having profound implications in building more fluent user interfaces for interacting with our machines.
Yeah, and these are the ones that a lot of exploration has already gone into. But Codex is also able doing code to code. One of the common examples that you may have seen is GitHub Copilot, where we're taking the code that's already been written, feeding it into Codex, and getting suggestions to speed up developers for what the code that they want might be. We can also explore looking into how to fix bugs and fixing that code in place, or even doing translations from one language to another, where you may have a legacy system written in some outdated language and you want to transfer that to something new.
Yeah, and there are also some really fun code to natural language scenarios we can think of. Making error messages more readable. I know that most of the errors I get are very difficult to decipher. You can use it to explain code, which is something that the Copilot Labs team has been doing. And then you could also imagine using code to NL capabilities to help author your pull requests or write your commit messages for you. Cool. So, in using Codex and in the examples we saw, we discovered a pattern for natural language to code.
Yeah, so to kind of show this pattern here, we have the Babylon example that we showed, where we start with a comment that kind of sets the scene and says, this is what we're doing. We're using the BabylonJS. Then we have a few examples of how to actually work with the library, where we say make a cube, and then we have make a sphere. And then after that context has been set, we can go into the natural language being submitted by users. We also saw the same pattern in Minecraft. This time we also had to include the API reference to teach it about something that it hadn't already seen. But again, you see, we set the context with exactly what this file should be containing. Then we give an example, in this case, move forward. And then at the end, we're able to tack on what the user actually wants us to accomplish.
We've sort of formalized this pattern as a pattern that we'll see in natural language to code interfaces. And we really think of it as setting that high level context at the top, and then giving some examples to let Codex know the kind of code it should be producing at any given point, and then really maintaining a kind of session buffer, where as you're interacting with the model, you are tacking on the language that you gave to the model and the code that it responded. And then as prompts start to get a little bit too large, you start to remove some of the earlier interactions. So the model effectively forgets the earlier things that you said as you go.
Yeah, I know that I found this pattern very helpful, and it really helps to drive through exactly what we want the model to do. And it also allows for that richness of reasoning over what you've already said, which has been great. So we would definitely recommend starting with this pattern for your applications.
Yeah, absolutely. Now, everything we've talked about so far has been through prompt engineering, but prompt engineering is not the only way that we can we can coax novel behavior from these models. Prompt engineering is certainly a great place to start. If you engineer prompts the right way and you give the right examples, there's a good chance that just out of box, GPT-3 or Codex will be able to accomplish the kind of behavior you're looking for. But prompts do have their limitation. Prompts can only be so long. So with the Da Vinci class of model that we looked at, prompts could only be about 4,000 characters. And that does mean that as your prompt gets too long, you might need to start removing things from it. It's why we mentioned the session buffer for this pattern. And then as you have longer prompts, the model starts to get quite a bit slower. So one alternate way to coax grounded code out of these models is a process called fine-tuning, where you actually bring a bunch of data specific to your domain and you retrain the model with it.
Yeah, and that definitely is very helpful as a technique, because let's look at the Minecraft example, where we have an API. In this case, we only have 4 new ones that we want to teach it. But you could have an API that you want Codex to learn that has hundreds of API references. We can't fit all of that into that limited 4,000 character buffer. But if you go through fine-tuning, which is taking the existing Codex model and then giving it examples of your data and the types of completions that you want, you can fill a version of Codex with all of the information that it needs about your custom API and then allow it to reason over that.
Yeah. And you don't need a ton of examples to fine tune a model. We found that just by giving 50 or so examples of natural language to code, we were able to train a model that much better handled very specific scenarios. It also doesn't have to just be examples of NL to code. You can also pass API documentation. You can pass code bases that use this code. The model is able to learn from unstructured data how to write new code.
And that is something very cool that originally Codex and GPT-3 were learned on different unstructured data. So kind of as we're moving into this fine tuning, we can use that unstructured data to kind of constrain the model and its outputs to what we want it to do.
Yeah, absolutely. So in this session, we looked at one actual live demo with Codex and BabylonJS. We also saw how we could engineer prompts for a non-player character in Minecraft. In Kevin's keynote this morning, you may have noted that there were several demos that we showed around Codex. And we're excited to say that we're open sourcing all of these demos. They are prototypes for how you can use the model. They all also use that natural language to code pattern we just talked about, where we maintain a kind of dialogue of conversation to code with the model, and it is able to accomplish new things after the fact. And the third one we didn't mention here is a natural language CLI interface. And this allows us to interact with PowerShell, Bash, or Z Shell using nothing but natural language. So you can say things like, what's my IP address? And Codex will translate that into the correct script in a shell in order to get your IP address.
Yeah, this is really exciting. I know that I'm excited to go into these repos and actually see exactly how they're all working and see what learnings I can take and apply them to my own projects.
So we'll finish off the way we started with a slide full of links here. At the top, again, as a Build attendee this year, you will get free access to these models or credits for these models. At Build in years past, we've given device giveaways. This isn't quite a piece of hardware in your hands. That said, it's one of the world's most capable machine learning models running on some of the world's most capable supercomputers. So getting access to this is fantastic. We've got links here for the OpenAI Playground and the documentation for using the Playground and calling the API. Of course, we have links here for the Azure OpenAI service, where when you've graduated from prototyping with these models, you can deploy them at scale. And then finally, we have links to each of those GitHub open source Codex repos that we mentioned on that last slide.
Yeah, this is very exciting. As we said at the beginning, kind of getting into the playground and actually playing around with them and figuring it out is the best way to experiment with these models and to see how stuff comes out. So I'm really excited to hear about what everybody who gets this credit is able to go and build and get the model to do.
Thanks, folks.
Thanks, everyone.